For over a century, physics has been split by an impossible contradiction, until one strange theory proposed that everything, every particle and force, is made of tiny vibrating strings. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings are incredibly small, estimated to be about a billion times smaller than an atom. According to the theory, different vibration patterns of these strings produce all the different particles we observe. Just as a violin string can produce different musical notes depending on how it vibrates, strings produce different particles. This elegant idea attempts to solve one of physics' greatest problems, unifying gravity with quantum mechanics. General relativity accurately describes gravity and large-scale phenomena like stars, planets, and galaxies. Quantum mechanics accurately describes the behavior of tiny particles like electrons, photons, and quarks. The problem is that these two theories are mathematically incompatible when applied to the same extreme situations. This conflict becomes especially apparent inside black holes and during the earliest moments of the Big Bang. Physicists have long sought a single theory of quantum gravity that could work consistently in all situations. String theory emerged in the late 1960s, originally proposed as an attempt to explain the strong nuclear force. Early versions of the theory were eventually abandoned for that specific purpose, but physicists noticed something remarkable. The mathematics of string theory naturally included a particle with properties matching the theoretical graviton, gravity's messenger particle. This unexpected discovery repositioned string theory as a potential candidate for unifying gravity with quantum mechanics. For string theory's mathematics to work consistently, it requires far more dimensions than the four we experience daily. Most versions of string theory require 10 total dimensions, 9 of space and 1 of time. Some versions, called M-theory, propose an 11th dimension, unifying 5 previously separate string theory variants. These extra dimensions are theorized to be curled up incredibly tiny, far too small for humans to perceive or detect directly. A common analogy compares this to a garden hose, which appears one-dimensional from far away but has a hidden circular dimension up close. String theory suggests our familiar 3 dimensions of space might similarly hide additional curled-up dimensions at tiny scales. The specific shape these extra dimensions take, called Calabi-Yau manifolds, could determine the fundamental properties of our universe. Different possible shapes could theoretically produce universes with different particle types, forces, and physical constants. This connects string theory to the broader concept of a multiverse, with countless possible universe configurations. Critics of string theory point out that it currently makes no testable predictions that can be verified through experiments. The energy levels required to directly observe strings are far beyond what any current or foreseeable particle accelerator can achieve. This has led some physicists to question whether string theory qualifies as legitimate science or overly complex mathematical philosophy. Prominent critics argue string theory has consumed decades of research without producing a single confirmed experimental result. Supporters counter that string theory's mathematical elegance and internal consistency suggest it captures something fundamentally true. They point out that string theory naturally incorporates gravity, something no other quantum theory has successfully achieved. Despite lacking direct experimental proof, string theory has produced valuable mathematical tools used in other areas of physics. These tools have found unexpected applications in condensed matter physics, black hole thermodynamics, and even pure mathematics. Some physicists view string theory as one useful mathematical framework among several competing approaches to quantum gravity. A major rival approach, called loop quantum gravity, attempts to quantize spacetime itself without requiring extra dimensions. Unlike string theory, loop quantum gravity proposes that space itself is made of discrete, indivisible chunks at the smallest scales. The debate between string theory and loop quantum gravity represents one of the most significant divides in modern theoretical physics. Some physicists believe elements of both theories, or an entirely different framework, will eventually merge into a complete solution. String theory has also inspired the holographic principle, suggesting our three-dimensional universe might be a projection from a two-dimensional surface. This bizarre idea suggests all the information in our universe could theoretically be encoded on a distant boundary surface. The AD/CFT correspondence, a mathematical tool from string theory, provides concrete examples supporting this holographic concept. This correspondence has become one of string theory's most celebrated and productively used mathematical achievements. Despite decades of research, string theory remains unconfirmed, existing as an elegant but unproven candidate theory. Some physicists remain optimistic that future technological advances could eventually provide indirect experimental evidence. Regardless of its ultimate fate, string theory has profoundly shaped how physicists think about the fundamental nature of reality. Whether the universe truly is built from tiny vibrating strings, or whether some entirely different idea eventually solves physics' deepest contradiction, the search for a single theory explaining everything remains one of humanity's most ambitious intellectual quests.